Hello, my name is Ajay Pillai, and this is my final project for CSCI E-89 Deep Learning for Harvard University Extension School. My project focuses on implementing transfer learning techniques for recognizing cartoon characters through their faces. The introduction to this project is that the recognizing cartoon characters presents a fundamentally different challenge from recognizing natural images like faces and objects and photos. Many modern networks pre-trained on large-scale data sets such as ImageNet tend to perform exceptionally well on faces and objects and animals. However, they tend to struggle in specialized domains for a myriad of reasons. For in cartoon domains, they have issues because such things like exaggerated proportions in the faces, simplified textures in the art, and like inconsistent color schemes that make it hard for the model to contextualize between different images. And on top of all that, there is a lack of data comparatively. There is no massive data set such as ImageNet, so you need to use other measures to compensate. And in this project, we will look at specific measures you could use to combat such issues like this. Specifically, we will be using transfer learning methodology to better adapt a pre-trained image recognition deep learning model for a specialized domain. And in this instance, being cartoons. The objective of our project is to evaluate the effectiveness of transfer learning for cartoon face recognition by systematically comparing multiple strategies and expanding on them. Specifically, we will establish a baseline CNN trained from scratch, and from there on, we'll assess performance gains achieved first through using a pre-trained VG16 model, the frozen feature extractor, and then we will examine further improvements by through doing implementing fine tuning the pre-trained layers and more aggressive data augmentation techniques and see if we can improve generalization. So here's the tools and environment used. Everything was written in through the Anaconda environment, Python 3.10. This is the data set used for the project. It is the iCartoon face data set. It's downloaded from GitHub. It has 389,000 images and with 5,013 individual characters. You can see a small subset of them shown on the right. Some pre-processing has been done already as that the all images have been accompanied with file names, bounding box coordinates on the detective faces, and individual character identity labels. The data set is already split into training and test sets provided by the authors. And key thing to note is that due to constraints from using local hardware, we will be only using a curated subset of 15 characters and 300 images for this project, which again will allow us to exemplify the issues of having a small data set and what need to do to combat it. Here's the architecture of the model. So cartoon faces are input, and then they can optionally be passed through different data augmentation techniques. Then they can either be passed through a baseline CNN or the pre-trained VG16 feature extractor, which then you can optionally also implement fine-tune techniques. And then finally, it is fed into a task-specific classification head, which will produce the final identity prediction label. Here's a code overview. Here's the imports we use for the code, mainly deep learning frameworks, it's TensorFlow, Keras, a couple numerical libraries, some utility imports. There's the data set root, class discovery, and labeling coding, ensuring that we properly labeled the images for best for ensure supervised learning goes smoothly. Here is data set construction. And we are left with, see, 4,500 images In the data frame has the file path, uh, the class name, and a corresponding numeric label. Here's the train val test split. Here is the image loading and data set pipeline construction. Key thing to note here is that the images are resized to a fixed resolution and normalized floating point values to ensure ease of standardization for training. Here's the baseline CNN architecture. Key thing to note here is that a dropout layer has been implemented to ensure to combat overfitting. Here's the configuration for training the model. Key things to know here, we're using standard to atom optimizer with a learning rate of 1 to the 10 negative third. We're using sparse categorical cross entropy as the loss function. Model performance is evaluated using classification accuracy. Uh, Key thing to note is that also we will be implementing early stopping and model checkpointing to ensure that model has robust training and to prevent overfitting. Also key to note that we will be implementing the similarly in all of the models as well. Here is making sure that we're doing another pre-processing for the images to make sure they're VG16 compatible. And then here is our frozen VG16 transfer learning architecture. Key thing to note is that the convolutional backbone is kept fixed for low-level and mid-level representation, and specifically for task-specific classification. Here's training the model. Here is the fine-tuning implemented on the model. Thing to note about the fine-tuning. Um, all layers are initially frozen to preserve the previous representations, and then the final convolutional block is only then unfrozen. So only a small subset of the features are updated. Uh, Here is the model architecture for with the model we use the strong data augmentation techniques. Key thing to note here, we're doing geometric transformations like rotation, zoom, translation, appearance changes through contrast, and horizontal flipping. Here's the training. And finally, we also included uh, an interactive model with a query interface to allow us to make more qualitative uh, ex examinations of what the model is doing and its performance. And it could be expanded, and this allows us to expand the model for real world usability. So here are the results from the model. Here's the baseline CNN. We achieved fairly good performance even from the baseline uh, test accuracy, approximately 89%. Test loss of 0.42, establishing that the data set can perform just with standard features and which gives us motivation that this is a good jumping off point to expand into further, improvements in the model. And so here then we have the frozen VG16 model results. It showed some improvements. It jumped up to 93%, fairly substantial 93.9. So, which overall, there's showing reduced risk of overfitting, higher accuracy, significantly, and while, and with a much leaner model, with significantly fewer trainable parameters. And since this is another improvement, we can say that we have again set a solid foundation for subsequent fine tuning and other techniques that again that like uh, this shows promise for improvement. And now we have our fine-tuned model and its results. And as you can see, that the fine-tuned model achieved a significant gain in performance, and it ended with a final test score of 97.18, which these results clearly show that a fine-tuning strategy is a very effective for maximizing performance on a relatively small structured data set. Finally, we have our model with the strong augmentation techniques. And as you can see, interestingly, the score went down to approximately 77.8%. Which is lower than both the frozen and fine-tuned variants. So this tells us that that there is a trade-off, that if you focus on augmentation, that it seems to increase the variability in the model. And finally, you have the results from the interactive model. The baseline does not do a good job at predicting very well at all. The the frozen fine-tune model does a pretty substantially good job at seeing it, and then the uh the augmented model also does not do that well. So, some challenges and how they were solved in this model. So, as mentioned before, there's the high interclass variability and interclass similarity. Like, there's a lot of stylistic variations and issues in the data set of just how these cartoon pictures work. So, and the solution was pre-processing to ensure consistency. And as a result of that, we've achieved a pretty robust model capable of a really strong score. Another issue that like is the limited data size that we've also like put on ourselves. So which made overfitting a huge risk from the get-go. And so that's why we have our stage training strategy with the frozen sorry, with the frozen model. So sorry. So I was able to extract semantically meaningful features. Um, the model evaluation beyond aggregate accuracy, so we just had the one score, or the one value to look at performance. So we were able to solve that by adding in the interactive model, or the interactive query that also gives the top K predictions. And then just the general issue of overfitting is mentioned earlier, and that was solved through attacking with dropout regularization. And finally, lessons learned, most important, data quality and curation, essential. The better, better your data is, the more you do, better you do pre-processing, the better, more scalable and reliable like your model will be. Transfer learning dramatically improve generalization. Like employing these techniques will have substantial improvements on your accuracy as shown through the modeling. Freezing versus fine tuning, careful trade-off. Yeah, to ensure efficiency versus overfitting. And finally, data augmentation should be calibrated for each domain versus just trying to do as much as possible, which is a poor idea. Yeah, and